if you notice on the left, New York has 24 power plants, and the living cell has about 100 power plants. They happen to be called mitochondria, but it varies, but that's a ballpark number. Population of the city is about 8 million, and we have these structures called ribosomes, which help move amino acids around and help with the construction of protein in the cell. So to say that an individual cell is as complicated as New York City is an understatement. I could go into some of the things. Besides, on top of everything else, those 8 million people, maybe 5 million work, the rest are just hanging around. Whereas the ribosomes, they're all working all the time. It's a different world here. So getting off the ground was very difficult in the days before science was very well developed. And 18th century, we didn't even get to atoms yet with Dalton. So our view of things it was really Aristotelian. I had a couple of slides I moved out of the way, but earth, air, fire, and water, those are the elements. And water means kind of anything liquid. And what is it made of? Well, we don't really ask questions like that. Whereas Dalton said, yes, let's look at the substances. And it's made up of atoms, and I think in some cases our goal is going to be to see which atoms. He knew that water, by the time he finished his experiments, and others, hydrogen and oxygen were what was in water. And ammonia, nitrogen, and hydrogen, and a whole bunch of other simple compounds. But that's the way you should look at a substance. It's made up of a lot of atoms or combinations thereof. And it's just a different point of view. But that wasn't here yet. We're a little bit too early. So this is a very confusing case. Scurvy was a worldwide scourge. Even by the way, we associated with sailors at sea. And that was really the great tragedy. A couple of million, they feel, were lost during the age of exploration. A lot of voyages, you might have 30% of the people come back if it was a year-long trip, because they would all become ill with scurvy. And what happens is, besides the symptoms of weakness, fatigue, joint pain, your teeth come loose, your gums are so painful you can't eat, so you're gonna die of something at that point. Now, life was cheap because sailors still went out. Many were impressed, that was forced to go sailing, but many just went out to make their fortune because occasionally that would come your way too. I just can't think of it as just life was kind of cheap. We think astronauts have a dangerous job. About 3% of the astronauts have gone up into orbit or tried to, have died over the last 40, 50 years. But half the sailors were lost, so it's a big difference really. On one of these trips where many people had scurvy, a doctor, Lind, decided to run a test. He had a whole bunch of scurvy people to test. He took a dozen of them, and he had a big list of cures. Over 2 weeks, they followed these cures. I don't have to read all of them if you want. I always like this one, a half pint of seawater every day. I'm not sure I can handle that. The last one at least has interesting ingredients. Well, one of the things he chose was 2 oranges. And over 2 weeks, those sailors all got well. So this looked like we figured this out. Even though we didn't understand it all, that we had it figured out. Well, when you go back that far, people don't connect cure with prevention. In other words, he saw it as a cure, but they didn't say, oh, if we give the sailors some kind of orange stuff enough beforehand, they'll never get sick. He didn't really make that jump. Eventually, he got to that, and he realized that you couldn't do this. Imagine you've got a big voyage. You might have almost 1,000 sailors, right? And if everyone's going to have 2 oranges a day, 2,000 oranges a day, and they're out for 2 years, multiply that by 700 and whatever. So it would just be a ship full of oranges. If they didn't run, they'd get away with it. So he decided to develop a concentrate. And what he did was to heat it, which turned out, we know, like after the fact, vitamin C is so reactive that as soon as you start heating it up to any extent, it reacts and it's no longer vitamin C. So it didn't work. His big potion, he thought he'd make his fortune. It didn't work. It completely discredited what he had done, so people didn't believe it, the citrus stuff. Now, it looked like the British, who were already depending on ocean going more than many other countries, that those big trips without tremendous casualties. Comes Captain Cook. He goes on voyage after voyage. We'll take a look. These are essentially, if you look at the area of the Earth below the equator, he's the one who mapped all the oceans. Now, there are there issues today, political? Well, he went to all these native populations, and they were changed forever, basically, by these visits. But the net effect, he still was this explorer, and very sensitive, by the way. If you read his journals, this problem of affecting local populations was something he was aware of. But more than anything else, he cared about his crew. He cared about the health of his crew, much beyond many other British ships went to sea. And they all had the terrible, terrible casualty rates. But in his case, we have 4 years, 70,000-mile voyage, no one died of scurvy. So he didn't really have a permanent cure, but he knew that sauerkraut, if he could hold of some sauerkraut, and he had barrels of that in the ship. And that's when it's a fermentation thing. It does have vitamin C in it, and it's not destroyed because you don't cook it. So they would use it if someone was really sick. They would use that. And there was another thing in much of the southern oceans. On the islands there was something called scurvy grass. You look it up in the Oxford English Dictionary. They talk about scurvy grass, and if you mix that with other food in small amounts, or the water extract of scurvy grass sitting in water for a long time, you get a significant amount of vitamin C. We know. But he knew that he'd get this anti-scurvy device here. Now, the question comes up is, why is it that Captain A lost a third of his people, or 2/3 of his people? There's one famous case. And Captain Cook didn't lose anybody. Well, the truth of the matter is, he was a commoner. The Navy didn't really like him. He joined as a seaman at 12. When he left school, he went to school until he was 12. It's almost like my dad, who I think he made it to 13. But his Captain Cook just joins as an able seaman, but he was very talented. He learned navigation and mapping harbors. In the French and Indian War, the siege of Quebec, he was the one who mapped out the St. Lawrence to help the ships coming in, the British. So they put him, he was only a lieutenant, and his first voyage, if we glance again at the red one, that's his first voyage. He's only actually a lieutenant, but that was so successful that they finally made him a commander. Even though he had this commoner background, which back in 18th century England, that was really a big deal. Class mattered. It still matters, but it really mattered then. Okay, so that's why I think he paid enough attention there. Now the Admiralty, they listened to all the stories about discovering things, but they were more interested in the fact that nobody got scurvy, because they knew then that the Brits, somehow or other, if they figured it all out, they'd be able to go to sea on these long voyages, and they would kind of rule the oceans. And that's what they did for 100 years. When they finally worked all this stuff out. The statistician was put in charge of the Admiralty for a while. He set up this one acid test. I shouldn't say acid, but it's a 19-week voyage to India, and they had enough citrus juice that every seaman had to have a couple of tablespoons every morning in front of a superior officer, because they knew the seamen, we don't want this, and we don't want to take this, and to assure that they actually took it. And nobody got scurvy. So it looked like we were in business. In fact, by 1804, citrus juice was part of the regimen in the Navy, just like rum. You got a rum ration, you also got a citrus juice ration. Hopefully you didn't drink them together, probably wouldn't be helpful, but so they said 1804 we had 200 and some odd thousand liters of juice that were carried on board. The Battle of Trafalgar, which was truly crucial, they felt it was strongly affected by the scurvy problem, because only the Brits had the citrus cure. Now, if we take a quick look, here it is, a chance to talk about the Battle of Trafalgar. Even if this were something about not even vitamins or whatever we're talking about, you can't go by this without. It changed the 19th century. I mean, Napoleon would have invaded Britain, and how much different would the world have been? Interesting. So we come to this the battle, and why do we think that the French and Spanish who were here on the edge, who were out here, they're all lined up for the battle. Now, Horatio Nelson is short of ships coming in here, 26 versus 33. So instead of just lining up, usually they just lined up and went boom, 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 and whoever, somebody won, somebody lost. But he decided to do what they call crossing the T. he was going to bring his ships in like this. The minus for that is that as you come in, since your ship would, your gun's only like, you see this gun is going out the side of the ship, you can only shoot up or down, that's it. Whereas these guys are all lined up. They can go boom, 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 boom. They can really hit your ship once you're within range and you can't fire back. So now he estimated that he was going to have like 20 minutes or so when his ships would really be exposed. But he knew his seamen were better. The big thing here is how quickly can I turn around? It's about 3 minutes if you're really organized with this gun with 5 or 6 men on the crew. Boom, 3 minutes, boom. But he felt that the French and Spanish would just not be able to match that. So once they got in close, the Brits would be okay. The bad news was the wind died down almost completely as the British came in here to cross the T. They said you could swim faster than the ships were approaching. So they really took a pounding. But of course, they finally got in, and they did win the day here. The only problem was Admiral Nelson himself, very aggressive guy. He's 47 years old, I think, at the time. He'd already lost an arm in one battle, so he's walking around with one, and he lost an eye in another battle. So he's ready to fight. In fact, if we look back at this, I said, I wonder where his ship is. They got all these ships. It's right here, it's the front ship. He's going to go right in. He's the admiral in the Navy of England, and he's going to get killed. He expected to get killed. And so he did get hit. What happened is ships would take a couple of sharpshooters and have them up on a platform, partly up a mast, and they would shoot down on the neighboring ships on the deck where the officers were, all of whom were in uniform, clearly marked. And in fact, before the battle, his other officers told him, look, you got to take this, you got all these gold awards and all this stuff, take that off, at least wear a plain jacket. He would have none of it. Well, the sharpshooter found, this is his actual uniform. It's in the museum in Greenwich. That's why the blue is a little bit faded and stuff. But so it went through his lung, into his spine, and he was kind of cooked. But he lived through the battle. And they kept giving him reports. And the last report he received, Admiral, we've won the day. We've destroyed or captured 19 of their ships, and the battle is ours. And so Nelson is dying. He said, I thought it would be 20. He was kind of an amazing character. So this is why you have to follow the square, big column with Nelson on top. So interesting. Okay. Well, the British go to town. We're going with citrus here. So they have colonies all over the world, and many are in areas where they can grow limes and or the citrus. They pick limes, they grow them, they make that part of the naval ration, and disaster. There's hardly any vitamin C in limes of all the citrus fruits. So scurvy came back, despite the fact that everyone was getting his lime juice and stuff, and it was discredited. The whole notion that citrus juice would cure scurvy was discredited, and the merchants, there were more and more merchants traveling the seas, other than the Royal Navy in the 19th century, and they didn't like the citrus idea. It meant they had to leave space for it, they had to buy it, they have it, so they kept saying, we don't think it works. So sometime in the 19th century, it really had been abandoned completely. So much so that we come to this other, most of us, anybody who's read about explorers, polar explorers, we have Mrs. Scott's group of 5 who left from the last camp to head to the South Pole. Now, their diet was questioned already. It's a famous book by Roland Hunsford, very fine book called Last Place on Earth. And he actually tells you their diet. And he shows that they were about 1,000 calories a day short. All Scotsmen, they were just going to get more and more exhausted as time went on and lose weight and everything else. But in the meantime, I was looking at, there's no vitamin C, there's no citrus, nothing that would contain vitamin C. So these guys now, they left camp to go to the South Pole. It took them 60 days to get there. Well, a month, you've already got scurvy symptoms. 2 months, serious. You've got the fatigue, joint pain. They were cooked. Not only that, they got to the South Pole. They found out Amundsen had already been there several weeks before. So they turned around and come back, and they traveled for 90 days trying to get back. But they kept getting more and more exhausted. They went less and less distance. And scurvy, they would have been serious scurvy sufferers along with the other problems that they had. And so none of them survived. So now, it's not until the 30s, Albert St. George here is famous for the DNA. He was the one who isolated DNA, but he also characterized the vitamin C as ascorbic acid. Here he is getting a Nobel Prize. And commercial pill, by the time he received the award, 1937, you could buy vitamin C commercially to take. So, but it took a long time, fully 2 centuries to get the whole thing right. All right, in the 19th century, now this is taking a step backwards here, it produced great advances. This is the laboratory of Justus Liebig, an amazing guy. There are 10 or 11 people working here, and they're all like postdoctoral students, what we call today. He had what was, you can only describe it as a graduate chemistry department. All people working on extremely important stuff. Military stuff, commercial stuff, just pure, well, let's see what happens when we mix A and B stuff, and nutrition. He concerned himself with nutrition as well, and he really developed. Germany was the leader. They set up pharmacology. It's really a German science, the way the whole thing developed, and he was a crucial character in this. There were two other figures, but he had this great mass group of workers on this whole problem. And by the time he was finished, the Germans were ahead in developing organic chemistry for 100 years. It took Hitler. It only took him a couple of years, but he destroyed the whole thing, basically. It just took a couple of years because it was more important to him to make sure that none of the Jewish scientists had a job than that they should continue on with organic chemistry and working. It's not a case that every scientist was Jewish, but you kind of cut out a lot of the meat of what you had. So he worked on diet, and he decided, he settled on this. Fats, carbohydrates, proteins, and minerals, and you've got what you need. He even had the ratio of amounts he thought would be appropriate and to keep you in good health. He even developed a commercial product, Liebig's soluble food for babies, the most perfect thing. It's in some mother's milk, okay? But not so fast. It turns out when they would do laboratory tests outside of his lab here and worked on with animals, they found out if they just had Liebig's food for babies, the animals would get sick and die eventually, okay? And it wasn't, unless you added some milk. And Hopkins, who eventually wins the Nobel Prize, he really studied this in detail. An astonishingly small amount of milk added to the insufficient diet is enough to make things okay. So even though you don't drink milk anymore, if you get up every morning and you have 5 or 6 ounces, it's probably a little insurance as to your diet being complete. All right, very here. The difficulty I have is, let me do this here. Let me start. I won't do that. Okay. Now, we're at the end of the 19th century. The Industrial Revolution comes to Southeast Asia, which is still Dutch. The Dutch still have a colonial empire then. This is a map from the time. And they're developing the rubber resource, plus there's some mining that's going on. And they had to bring in thousands of workers. They came from India and hold on, we see them here on the left arriving, this boat. You can see how crowded things are, working on what would be a processing line. And it was like the ideal situation for disease to pop up. And there were many diseases that popped up, but in particular, beriberi came to the fore, and many people were sick and dying. It affects you neurologically, cardiovascular problems, serious disease, ultimately death eventually. And so we had this issue, and a scientist, Christian Eichmann, was sent out from Holland to the Dutch East Indies to see if he could figure out a solution to this problem. Now, he had worked with Robert Koch. Now, once upon a time, if you had come to my lecture about 19th century medicine, Robert Koch and Pasteur developed the vaccines and the bacterial theory of disease, and he was trained in this, and he was sure that there was a microbe that was causing beriberi, and he was going to find it. Well, first he worked with monkeys and rabbits, and nothing much happened. It didn't work out. He couldn't make them sick. But he found out they also had some chickens around, and he heard that some of the chickens were not well. So he picked some that were still well, and put them through some paces here, so a test group and a control group, and What he found out was they all got sick. They're not dead. Don't worry about this. They're not feeling well. So the controls and the test animals both became ill. So, you know, what's going on here? He's scratching his head, trying to figure this out. And then, magically, they all got better. He didn't do anything. They all got better again. So, as he said, I have a couple of quotes here. They're from his Nobel Prize lecture here in 1930. He did this work in 1880 or so. Okay, so he said, fortunately, suspicion fell on the food right away. And he said the new cook, it turned out, was stingy about rice. The old cook of the regular hospital kitchen didn't mind giving the extra white rice to the caretaker for the chickens, and they were all getting sick. But then this new cook, he said, "Oh, this is military rice. Those are civilian chickens." That was actually so he cut them off, and that's what really allowed us to move ahead and figure out what was going on, because essentially what went on is the white rice was it was new stuff, the white rice. But part of the Industrial Revolution issue, bringing in thousands of workers, meant they built a giant plant to process the rice. And they could mill the rice down so you got the nice stuff like we can buy today in the supermarket. It keeps, it looks good and everything. But what you're losing when you lose the brown coating, which is still left to some degree when you manually process the rice, is that the B vitamins. But he didn't know that at the time. In fact, at first he thought, here was his explanation. You don't get the, he said, oh, this must be poison. And apparently if you eat something with the coating, it has the antidote. And that's why you don't die. So it's not so obvious. We say, oh, look what it says, and we think we know what the conclusion is. But these guys had to think pretty hard about the whole thing. Eventually, though, he had this, he got the picture as to what was going on, that there was something in the coating that was completing the diet so that you didn't get sick anymore. So he said there have to be some accessory food factors that you need in extremely small amounts. Now, there's much that goes on here, but 1912, Casimir Funk of Hull, working in London, he isolated a material from the brown rice. He thought it was a pure stuff, but it was a mixture of B vitamins that he got. But it was one that would cure beriberi type illness, and did work as a curative. And he introduced the word vitamin. He had an E on the end. We've lost the silent E, but we kept the word. Now, there's a lot of chemical arguments for why he shouldn't have called it vitamin, but they're not worth going through. Okay, so Funk stuff prevented disease, and as I said, several B vitamins. And he, in his work, he eventually concluded that all these other diseases, besides beriberi, pellagra, scurvy, and rickets, they were probably all nutrition diseases. And his extract from the brown rice, he could also reproduce the same effects. Vegetable products, milk, egg yolk, and meat would also help complete the diet. So, all right, so that's our beriberi. Next, pernicious anemia. Pernicious anemia, whoops. No. There we go. Pernicious anemia was always fatal. 1907, they started following 1,200 patients, and within a year to 3 years, they were all dead. Okay, it's just, there was no way out. It was there were other diseases like that at the time, but you would be maybe in a hospital, but in kind of an area where they just kept you quiet and ameliorated pain and stuff, but you just were not going to get better. So I just have two personal stories I bring up. The first is my mother, when she was a kid, maybe 10 years old, her mother would give her a little note to the butcher, can we have some liver for our cat? And if she went to the butcher and it wasn't so busy, in the old days you had the sawdust on the floor in the butcher shop, some of us might remember this, and she'd give the note over, and the butcher, if it wasn't busy, he was always nice, wrapped it all up, and she'd have this steak of liver for the cat. Because a human being would not eat this stuff, really, you know. However, what happened, the second story is this. Again, it's the story from my mother, and this is one, by the way, probably from a Sunday Times magazine or something. This man became ill. He had a number of symptoms. We don't have to went to his doctor a few times. The doctor said, look, I hate to tell you this, you have pernicious anemia. and maybe you have a year or two to go, but you're in deep trouble. You're just not going to live very long. And the doctor said, you know, if there's anything you ever wanted to do in your life, you still get around okay now, why don't you go and do it? He said, well, you know, my brother has a dairy farm up in the country in upstate New York, and maybe I'll just go up there for a while and see. Well, the man had a business, successful business, so he sold off his business. You know, he's on the way out here. So he goes up to his brothers, and the doctor forgets the whole thing. He's kind of said farewell to this man. Well, a year later, he comes in, he gets a list of the patients waiting to be seen, and there's this guy, the same man who he had pronounced a death sentence to, really. And the man comes in, he's completely healthy. He's even lost his extra weight in his belly and all that stuff, and he looks great complexion, and he's mad. He's really mad. Doctor, what did you do? I'm not sick. And I sold my business. I got nothing. I like being on the farm, but I can't spend my life up there. And so the doctor says, stop, sit down a minute. Tell me about life on the farm. And he goes through how they were very active and busy all the time. And he said, well, what did you eat? He said, well, you know, I really thought at least I was going to have good food up there, because I know my brother, you know, he'd have to slaughter cows occasionally. And we got steaks, all that meat. And I said, my brother would sell all the meat. It's not, you know, dairy farming was tough, even back then, 100 years ago. So, but he'd keep the organ meat, and we ate liver. We had liver and bacon for breakfast, liver and onions for dinner. He said, I ate so much liver, I don't want to see another piece of liver the rest of my life. So the doctor actually had a university connection, and he called up this professor he knew, and he told him the story, and he said, you know, we're just starting to work on that idea right now. That they actually looked into this, and this, let's see what the scientists were actually doing. It turned out during the First World War, there were so many artillery shells fired, any decent sized battle, there would be 1 million shells fired before the charges would occur. The amount of shrapnel was unimaginable. So men would get wounds that weren't really fatal. That is, they might be peripheral wounds, but they'd bleed so badly they would die unless they got immediate assistance. And so it was a symptom of the First World War that we had this kind of problem here. And so this one researcher said, look, I'm going to try to see if I can't find the best way back to health for an animal, in this case, that loses a lot of blood. So he picked dogs, and he would bleed them down. They were really quite ill. And then he would start different diets. And what he found out was that just liver was liver won, hands down, that they would get better faster. Now these two gentlemen, two doctors, Mina and Murphy, decided, look, let's try this on people. There's no hope for these people. It sounds horrible, but let's do it. And here it is. Here's the first treatment for pernicious anemia using liver. That's a dinner plate, and that's a big chunk of raw liver, 12 ounces. You've got to eat that every day, for 4 weeks, and to see what would happen. Now, the picture is a little fuzzy because it's from the actual 1934 film, which was shown when all three of these men won the Nobel Prize, and it's just not very sharp. Usually, Nobel Prize lectures, they usually don't come with videos, so, but this 1934 one did. So, here's what happened. I do have to mention this, that part of the reason everybody can get pernicious anemia all the time is some people are missing some enzymes in the digestive system that pre-digest the B12, which is, well, I'm giving you the answer at the end. We don't know it's B12 yet. So that it gets absorbed into the bloodstream. So that's one of the things that happened, and it made the whole thing a little more complicated. And they were able to find that out and find which people face that problem. You could usually overwhelm it in the beginning. Having 12 ounces a day, even if you only absorbed a small amount of it, because you only need micrograms of vitamin B12. So, okay, so here we go. Here's a little more from the video, and I'm sorry it's not, as I said, a little bit nicer, but here's the man before. He was sitting in this chair right here. He's trying to walk across the room. He has no sense of balance. He couldn't really stand up on his own anymore. So he's got his arm around the nurse, and notice there's his hand coming around. It's not like she's guiding him. He would just fall to the floor if she were not there. Here he is 4 weeks later. He's out walking. He's just come down a flight of stairs, by the way, unaided. So, I couldn't get a decent still of him on the stairs. But he's walking, he's got this cane, but it's more like a Charlie Chaplin cane at this point, you know. Little extra insurance, but he can really get around. This is after 4 weeks. So it definitely worked. Well, people didn't like the idea of eating big chunks of liver, so they brought in some chemists to make extracts from the liver, and eventually they found one that was just as active as eating a piece of liver. And if you got a series of injections here, you could produce the same cure. And even to this day, the people who have the most difficulty absorbing B12 can get injections here of the liver extract. This is one more graph. This is a case of, here's what happened. We had almost no red blood cells here, and these are two different injection treatments that bring us back up. So these are days going by. Within a few weeks, we're back up to normal. Now, we still don't know what it is that's doing this, but in the 1940s, we come to the amazing Dorothy Hodgkin. We actually saw her before in one of our other discussions. We talked about penicillin. She was the one who figured out the way the atoms are arranged in penicillin, competing with like at least 1,000 other scientists and a whole bunch of big labs. She was able to do it. Remarkable woman. Okay, so this is the structure. We don't care that much about it. It's so complicated. But notice there's a cobalt atom in the middle, which is kind of interesting to me. Of all the molecules in your body that you need to function and operate, this is the only one that has a cobalt atom in it. Otherwise, we would not need cobalt as part of our diet, except for this vitamin B12. Well, all of a sudden we're going back in time to the origins of life, because we got this problem. Nobody can make B12 except bacteria. There's no other animal. It's not like vitamin C, where most animals can make it, except people and guinea pigs, and a few others can't. But nobody can make B12, nobody in the animal kingdom. So we depend upon the bacteria. So here we go, the origins of life way down here. The first thing that comes along are bacteria, and there are several of them that can make vitamin B12. And the fact that they can means, as you go along, that we can have animals. We're not going to have the animals without vitamin B12. It's a remarkable thing, but we lean on these ancient bacteria to move us ahead. Those of you who think like science fiction and will find life in other places, it's going to be pretty sneaky. It won't maybe not be so sneaky to find life like bacteria and these guys, the relatives of the bacteria. But to have something like we see on Earth, our animal kingdom, it may be another big jump or two more difficult to do. Okay, so here's what happens. The ruminants happen to have this complicated digestive system, and they're loaded with B12 bacteria. Those bacteria that crank B12 out. So anything that has to do with a cow is going to be a good source of B12. The milk or the cheese or the meat itself. On the other hand, a bad source, chickens, are not going to work out well. Occasionally this chicken might pick up a little B12 from the ground as he forages for a seed, but not to the point where chicken meat it's not going to be a good source of B12. So, in any case, that's our B12. Now, the bacteria, since I mentioned them, they did something else to really help us. Way back when, 3 billion years ago or more, there was almost no oxygen in the atmosphere. So any life that existed would be extremely simple and minimal. And along comes the cyanobacteria. They should have statues of cyanobacteria. They do with old generals and stuff. Well, it figured out photosynthesis. In other words, it could decompose water and make oxygen. That's supposed to be later. Yeah. No, I'm kidding. So what happened is, over 500 million years, the cyanobacteria brought up the oxygen content to where it is today, the 20%. And what this allowed to happen was for multi-cell animals to be made. In other words, I take a deep breath, I take in a tremendous amount of oxygen. I'm made up of 30 trillion cells, and somehow I have to supply them with enough oxygen to run the reactions to keep me alive and make it through the talk. As long as we got the slides up and everything. So we depend on the bacteria again. The cyanobacteria, the fact that these guys figured out how to decompose water, they filled the atmosphere with oxygen, and so we could really have the animal kingdom, the lions and the tigers and the mice and the snakes and all that. Without them, the world would just be, we might get here and say, oh, the astronauts say, well, we found some life on this planet, but I can only see it under a microscope. And if it was 0% oxygen in the atmosphere, that would be the case. All right. Most concerning case, see if we can get through here. And that's why their diet was okay. So, he got that. Now, he went back, he knew the Europeans, like Funk and others, had already looked at the water part of milk. In the old days, you used to see milk separated to curds and whey and stuff. They worked on the water part, and he said, well, look, I think that this agent, I'm going to look into the milk fat. And he was able to isolate what we call vitamin A in his work. And it has a key function in vision here. But we have to stop a second to realize today what the problem is. Vitamin A deficiency is the #1 killer, basically, in the world. It's more than AIDS, tuberculosis, malaria, and these numbers are 2010, so I'm sure this number is well over 3 million a year. And it's just horrible to think that this is the case. So this is the tough part here. A little bit of science here. It turns out that vision. We all know that vitamin A is associated with vision. I hope. Bugs Bunny, all that kind of stuff. I'm sure. Your mother or father. They should have talked to you about it. I'm sorry if you missed it. Okay, so what we notice is this: is that light. I think we most heard of this. UV. We worry about UV. We have visible light, and then we have infrared, and there are many other parts of the spectrum as well. But we do know this: that UV is kind of dangerous. It causes sunburn, and that's a worry. Sunburn. When I was a kid, the first thing you did on the hot days, you went out and got the worst sunburn you could, and you peeled, and you would tan. We weren't too worried about skin cancer, all that stuff. But when the skin peeled, you had killed all these cells with the ultraviolet radiation. That's basically what was going on. Now, in the case, the vitamin D3, I'm going to have to let that go in order for us to get through. That was only a few seconds anyway. But so the idea is this. On the other hand, the IR does not. It's not dangerous because it's warmth. What it does is it tends to speed up the molecules. If you walk out into the sun, the molecules of water start speeding up in your skin, and you have that feeling of warmth. That good feeling. Don't feel bad. It's just a bunch of molecules speeding up, but it still feels good, just as a human being. Now, what happens with the visible light? It's in between. It doesn't break all your bonds. If it did, then every time you looked at something, your retina would be destroyed. So it can't, the visible light can't be doing that, but it can run chemical reactions, and it can run reversible chemical reactions, and that's really the key to our vision system. We can't do all of this, but here's vitamin A, and what happens is when sunlight hits it, boom, it undergoes this reaction, which I'll represent another way, and it turns into the dead, inactive form of vitamin A, but enzymes can turn it back into the active stuff. But let's look at it in a symbolic way. The molecule that's active is kind of like this, crooked. It's out of this way, it's out of shape. But when it turns into the dead stuff, it goes like this. It actually straightens out a little bit, and then the enzymes go to work. This happens almost like 1,000th of a second, something like that. But bringing it back to the enzymes might take a good fraction of a minute. And you've noticed this. Everybody here's noticed this. Because sometimes, now normally what you want to have happen is within the megapixels on your retina, you want not all of the vitamin A to react at once, because you've got to get the next picture. The 30th of a second light, you've got to get new pictures. So you've always got to have some of the stuff that hasn't reacted on your retina, or else your vision system's not going to work. So occasionally, if a flash goes off in front of you, film flash, you go like this, and you see this dead spot for a while with your eyes closed. It's not working. Those pixels in that area where that flash went off, you got to wait. The enzymes take time to do all this stuff. So, how long does it take before your eye feels you don't see that dead spot? Fraction of a minute or so, half a minute usually to get back to normal. But that's something you've all experienced this. I just know. I mean, and accidentally you might look too close to the sun by chance. And similar things can happen. The other extreme is this. Let's say you don't have any vitamin A, or you don't have hardly any vitamin A in the pixels on your retina, so you don't have any of this stuff. So the signal that's produced, in other words, when this change occurs, boom, energy's given off. some of it produces a nerve impulse that goes up into the brain. And but if you don't have any of this, the signal gets so weak you don't get anything unless you're in a really bright room. So you get what you call night blindness. If someone really suffers vitamin A deficiency, that's something that comes up, which we can simply. So we're out to get. Look, we got to get hold of this molecule. So I'm going to move this whole structure over to the next page. Here it is. I shrunk it a little bit because I want to find a couple of a molecule that will have this in it. And amazingly enough, something I'd also heard of, carotene. Carotene's in carrots, tomatoes, canaries, turnips, marigolds. But we usually don't eat canary feathers and stuff. So what you do is take this carotene and cut it here, cleave it here, right, chemically, and put a little oxygen on. You got a vitamin A. You're all set to go. Plus, if you look at the other half of this molecule and notice that it's the same as the other one turned upside down, that you get 2 vitamin A's for every carotene. So this is a good, this is our chemistry lesson really for today. Now, let's take a look at the story about vitamin A and what we're going to do. Red is bad news, and the undeveloped world tends to be more in trouble here with vitamin A deficiency, and we have to find a way to improve this. And leading cause of childhood blindness, weakened immune system. 2012, WHO says there's 250 million preschool children are affected. They're on the way to illness because of weakened immune system. They're on the way to blindness and eventually death if they're not healthy. So we have a significant tool, and it's called golden rice. And this is the one, politics, I'll be shot down, but let's just consider this for a moment here. Here's white rice. Now, if you take, it's like 3 genes from the marigold that make vitamin A, and splice them onto the genome for regular rice, then you can make this golden rice, which is loaded with beta carotene. And the idea is you'd have to get the farmers to plant that rice instead of what they normally use for the vitamin, because this is the only way to get at it. You can't say, well, we're going to send a whole bunch of vitamin pill bottles to somewhere. It's not going to work. It has to be inculcated into the whole way that things proceed. All right, so, but we do have the problem. It is GMO, and so it's been fought tooth and nail by Greenpeace. They've been preventing countries from growing this. They had a big victory recently in the Philippines, which is all set to start using it, but the Supreme Court, based on this Greenpeace suit, didn't allow it to happen. And this, of course, these are only Nobel scientists and stuff, but they suggest that how many poor people in the world must die before preventing golden rice from being planted is considered a crime against humanity. So, all right, last one, most insidious. See if I can get through with this. Nice rural village in China. We can see it's set up for agriculture and stuff. And when you go to visit one of these rural villages, everything looks normal. There's a row of poplar trees, some nice lined houses, but eventually we start seeing these heads sticking out of windows or around the side of houses. They look like adults, but their faces are kind of flat, expressionless for the most part. And they are the Chinese many creeds. It happens a tremendous number here in the rural areas of China. And the question is, how did this happen? What's going on? It took a long time for us to get any sense out of what was happening here, because the Chinese Revolution, Chairman Mao took over, and then Mao had the Cultural Revolution, and then they had Lysenko theories, and 45 million people died. And when the smoke finally cleared, not so long ago, they set out to see if they could address this problem of what they call villages of idiots here. Now, they thought there was some genetic issue, and the reason was you have a village here, 2 villages here, 2 villages here, and they all have many people with neurological impairment here. So they said there must be a couple of genes, maybe, genetic defects. So they brought in some biologists, and no issue at all, no problem at all. Then they noticed that they all used the same salt source, which was nearby. In other words, here are the villages, there's their salt source, and they get it. As they analyzed that, they found that it had no iodide at all. And it was the lack of iodide that caused this neurological problem here. Lifetime neurological problem. No turning back. You can't correct this. So they knew in the 1920s in the U.S., they were in the Midwest especially, if you're away from the ocean and your salt source is away from the ocean, it's less apt to have iodine in it. And they were goiter was a big issue, and other symptoms that you could have from vitamin A deficiency, particularly in the Midwest. So that the government suggested that they iodize the salt for daily use. They never regulated it. Okay, so you don't have to. In other words, all the salt sold doesn't have to follow through here with iodide. But if you have iodized salt, at least you can avoid this issue here. So, all right, it's crucial to brain development. To me, this is so disturbing. The first time I read it, it's so vital in the beginning. That first couple of months, you're cooked if you don't have iodide. I mean, the rest of your life is circumscribed from that problem. All right, let's look at what we see around the world. We notice that the undeveloped countries, it's there, but now Australia, New Zealand, we've got Russia, okay, so we've got Italy, Spain, into Europe, the countries where there's not sufficient iodine in the diet of many people. This is a real issue here. And okay, here's information that was gathered in New Zealand. They started to notice this problem. They went from the 80s up into the 2000s. This stops in 2004. They're still working on this, but this is a histogram. I think you've hopefully seen histograms before. There were two lines. One is the line of how much iodide you want to ingest each day if you're a pregnant woman or might be pregnant, might become pregnant. And the other is the amount that you want to have just to be a healthy adult here. So in the beginning, when they looked, everybody was okay here. Even when they brought the kids in, the green is the kids, yellow men, blue women, green kids. But then things started to get worse here. And we finally got to the point in the 2000s, nobody's getting enough iodine. Now we can worry about it a lot for the kids and adults, but the fact that the pregnant women are way down below what we need, with a woman who might become pregnant, childbearing age, this is, it really is a significant problem. Now the New Zealand government has made some adjustments. They forced the bread makers to include a process so that there would be iodine in the bread, and a few other things. They keep revisiting this because it's not getting better right away. It's not getting better right away. Here's another case that, again, developed world. This is Denmark, Skagen, and Randers. Skagen has really good iodide content in its local water, and Skagen doesn't have any. And this is a graph of survival rate of the population, all causes over 20 years. And what happens is if you've got water with iodine in it, your survival rate is better. The best way to look at this is horizontally. You can see that there are years of difference between the survival rate here in this case, okay? So they're addressing this in 2019. They actually regulated iodine and salt. So this only runs up to 2018. Now, some tests in Europe. We've had IQ decrease. When we would test, if we would find low, this is in kids, now school kids. Low iodine, we'd find definite, over 10, 15 points. Decrease in IQ. Auditory threshold increases, you don't hear as well, even a youngster. Motor response, reaction time for kids. And then finally, even ADHD frequency, something that's a little harder to judge, but it's just amazing. Here's finally one thing from the United States. This is Lansing, Michigan, around 2020. And it's only women now. Young women seem like they're okay here. These guys are okay, but the women of childbearing age, 20 to 39, seem to be below. They're actually below what you should have if you're, a pregnant mother. So that it's a problem that's growing here. Now, why? What's happening? Where did this all come from? Welcome to exotic salts. All right? Here is an example there. I can't pin this down except for New Zealand. And New Zealand said just this salt alone is responsible for about 1/6 of all the iodine deficiency problems in the country of New Zealand. Okay, so I actually went to the salt store and asked them about what's the iodine content of the salt. You said, they don't know. Why would you ask me a question like that? It's like that's one of the things. This fashion salt. Somehow the fact that it doesn't have iodine is better. Terrible mistake. Terrible mistake. Okay, finally we've got this pregnant mothers, spontaneous abortion, stillbirth, and the neurological consequences. For the elderly, it turns out they've done studies. If they test the iodine in your urine, the lower it is, the more apt you are to have some cognitive impairment. So at all ages, we should be having, that should be, you buy a multivitamin, it should tell you how much iodine is in it. They don't generally. The prenatals, at least the ones available here do, at least they let you know that they've got the iodine in them. Okay, you know, I showed these slides to Judy. And she, what are you talking? Nobody knows about this stuff. You know, what are you making all this up? So I had to think. This is the main scientist in for the WHO 2023, and the reason this is a problem is that the general public doesn't know it, the authorities don't know, the health professionals don't know, and the food producers don't know how important iodine is. That's the way it is right now. So, okay, all right. Bear with me for just 2 minutes more. I think you might find this interesting. It has to do with a molecule that contains iron. Now we know one. Again, if you had been to one of our other talks, we talked about hemoglobin, which of course you all know contains iron. But there's another molecule called cytochrome C, which contains iron. Now this happens to be, to make it a little more friendly, it's an artist version, so it's not a real chemical thing. But what the main point the artist is trying to get across here is that the heart of this molecule, which is highlighted, is vital to every animal on the planet. Whether it's a really tiny guy or a big guy, you've got to have this important central part of cytochrome C. But these guys on the outside, they can change without having any effect, okay? So this is now the molecule, okay? I just flattened it out, right? Mm-hmm. Here's the yellow part in the middle, and here's all the blue. It's an Excel spreadsheet, right? In fact, let's put them next to each other. Here are the outer cells, here are the outer cells. There's the iron in the middle, there's the iron in the middle, and here's the other guys that you need around that. So now what happens is, if we compare, everybody's got cytochrome C. Your cat, your dog, your hamster, they've all got cytochrome C. But every different species can have a different amount, because by random mutation, any one of these blue guys can change. So you can get an idea of how closely related two species are by just counting the differences. Now, we're going arbitrarily, I'm going to use human beings as a reference, and I picked a couple of animals where I've just counted how many of these blue things are different from human beings. And here's what we got. First, I've got the chimp. Well, we knew that we were related to chimps. Cytochrome C says, yes, you are, because our cytochrome C is the same as theirs. By the time you get to the snake, as a representative of the reptiles, we've got 14 differences. It's a little comforting to see that they're really far away from us. Fish will go even further. And finally, I keep thinking of the movie The Fly. The Fly, we have the 29 differences, which is also a little bit heartening. Well, if you look closely at this, and since the mutation rate is random, we find that every one of these differences represents about 20 million years of separation on an evolutionary scale. So I can take these pictures and put them right on a graph. Now this graph, these differences, like you see the chimp here at 0, he's down here at 0. Here's my snake at 14, my tuna fish at 20, and this guy at 29. And over here we've got the years that we separated on the evolutionary timeline. And to me, I'll tell you, I first saw this, I remember it was 1968, I saw this, the history of life on Earth described in significant detail by one molecule. You know, I said to myself, man, I'm majoring in the right subject. That's the way I felt, to be honest, at the time. At least it's going to be useful to me, and I found it to be an interesting thing. I don't know if you do. That's our story. Thank you for sitting with me through. And Tom, thank you.